the amount we're going to read on this iteration of the loop, bytes to read, is if there's a lot of bytes left, i.e. it's bigger than the size of our temporary buffer, then for now we'll just read in one temporary buffer's worth. Otherwise we can read in the whole lot if there's less bytes left than the size of the temporary buffer. So that's how many bytes we're going to read on this time round on the loop. So now we can call read process memory, and first we pass the handle, then we pass the base address in the process we're looking at, plus how many we've read so far. So it starts off as 0, so the first time round we'll just get it from the address. And then our local buffer, the amount to read this time round, bytes to read, and this will be filled out by the function how many bytes were actually read. And if there was a problem, bytes read for some reason is not what we expected, then we'll just bail out. So now we've read a block into our temporary buffer, so now we'll copy that to the actual buffer that we allocated in the memory block structure. So it gets buffer plus total read, and it's from the temp buff, and the amount to copy is bytes read. And then we just update our loop variables for next time round. So bytes left gets the amount subtracted off it, and total read gets the amount added on. Now you may be wondering, why bother calling read process memory into a temporary buffer only to then copy the temporary buffer into the real buffer? Why not just read directly into the real buffer? Well, if all you were interested in was what this is doing, a straight copy, then yes, you could do that. But ultimately we're going to want to compare the new values in the memory to what was there previously. So we want an intermediate stage where we have the new read values in a temporary buffer, and we can then use that to compare with what was previously in the buffer, but we haven't implemented that yet. But that's why we're using a temporary buffer. It'll become more clear later when we start implementing that side of it. So that's our loop, and then after the loop we'll just update the size to total read. This means if there was a problem and we, for example, only managed to read half the amount we expected to read, we'll update that there, so that this will then reflect that the other half of the buffer is no longer valid. But that's our update function, so that'll update one block. So we want to do that once we've created a block, so we can just put it in there. Like that. So when we've created a block, the first thing we'll do is update it to read the initial contents, and for later use we'll have a utility function that will just update all the blocks in one list. So we'll call it update scan, and it will take the head of the linked list, and we'll get a local pointer, and we'll just update each individual memory block and move it to the next one. So that's for later use when we just want to update an entire block list in one go. So now that we're actually reading memory in, we can modify our dump function to dump the contents of the buffers we've read as well. So we'll just make a variable called I. And once we've printed out the base address and the size of the block, we'll print its entire contents. So we can do this, and let's read each byte and print it. And we're done, print a new line. So that's going to print out an awful lot of data, but it will allow us to see that it's working as we expect it to. So let's try and compile and run that now. Total read undeclared, line 53. I called it total left, that's why. Let's try that again. Argument 5 from incompatible pointer type. I suspect it's because it's expecting a D word pointer, which really is just an unsigned int, but they probably type def it as an unsigned long, so it gets treated differently. There we go. So actually, what was the notepad process? That. So as you can see, that's the contents of the notepad process. So it's a lot, but that appears to be working okay. So now we can begin implementing the search functionality of our scanner, and we need a new buffer, and we'll call it search mask. Now the idea of search mask is that it holds a flag for every byte in the buffer, and the flag decides whether the byte should still be included in the search. So at the start you would search every single byte, so every flag would be set. Then all the bytes that didn't match your first search, you would clear their flags, and then the next time round you do the second or however many subsequent searches, you know which bytes in the buffer still need to be searched and which ones are to be discarded based on the state of its corresponding flag in search mask. So to go with search mask, we will just keep a count of how many matches, how many search matches are still in this memory block, and we'll also make a variable called data size. Now this can be 1, 2 or 4, and we'll use that to decide whether search comparisons should be done on a byte basis or a word basis or a D word basis. So in our constructor function we need to allocate for this new buffer. Now that would work, that would be fine, just allocate 1 byte per byte in the buffer, but it's wasteful because we only need a true or false value which can fit into 1 bit, so we can keep 8 flags worth in a single byte in search mask. So we can divide how much memory we need by 8, and at the start we'll set every flag to true, FF, in that byte. Like that. Now it does make it a little trickier to keep track of the flags because each byte of the search mask now contains 8 flags, so we'll make a couple of helper macros